let's use Kirchhoff's rules to solve some circuits. All right, so let's start with a pretty simple circuit. Suppose that we have a battery like this, and then a resistor over here. And let's say that we know the values of the components. So the battery is going to be 1.5 volts, and let's make the resistor 15 ohms. Okay, so let's say we know those two things. Well, in order to use Kirchhoff's loop rule, I need to define a couple of points around the circuit. So let's say that I pick these 4 points, and I call them A, B, C, and D. Okay, well, if I use the loop rule, then delta V AB plus delta V BC plus delta V CD plus delta V DA all add up to 0. That's the rule. Okay, and the delta V from A to B is just going to be 0 because there's just a wire connecting them. So delta V for a wire is equal to 0. And that's also true for CD. So between C and D, nothing interesting happens. The potential difference is 0. So as we go, you'll see that we didn't really need to include A and B as separate points or C and D as separate points. We could have just picked one point on either side. But this is mostly for illustrating how this works. Okay, so the delta V from D to A is going to be 1.5 volts. That's what a battery does. So we know what the potential difference is because we know what the EMF of the battery is, 1.5 volts. Okay, so that one's easy. And then the last one is delta V BC. So we want to find delta V across the resistor. Well, how do we do that? How do we figure out what the potential difference is across that 15 ohm resistor? Well, we can use Ohm's law. So delta V BC is just going to be the current through that resistor times its resistance. Okay. So we know the resistance is 15 ohms. We don't know what the current is. Something we need to be a little bit careful about, though, is whether this is going to be positive or negative. So Ohm's law only tells us magnitudes. It doesn't tell us direction. So because Ohm's law only gives magnitudes, we're always going to have to consider whether it should be positive or negative in a given situation. So, which way is current flowing through this circuit? Well, the current is going to go this way here, and then it's going to go down through the resistor, and it'll go to the left here. So the current is going to be going the same way around the loop that we are. We're going from A to B to C to D. When the positive charges that we're imagining flowing through the circuit go from B to C, they're going to be going downhill, so to speak, in the hill analogy. So because the positive charges are going from a higher potential down to a lower potential, this change is going to be negative. So we need to include negative IR here. So delta VBC is negative I times 15 ohms. Okay, so we don't know what I is, but we do know the relationship between all of the potentials in this equation. Okay, so I can take negative I times 15 ohms plus 1.5 volts equals 0. So now if I solve for the current, I get I equals 0.1 amps. So in this example, you can see how we use the loop rule. We write down a relationship between potential differences, some of which have unknown quantities in them, and then we can solve at the end. Okay. Every time we are considering a resistor, we'll have to figure out whether the potential difference is positive or negative. You might also wonder, what about the battery? Like, we just wrote down positive for that. Well, again, we were going sort of up the battery. So that means that as the positive charges go from the lower potential side of a battery to the higher potential side, their energy has increased, which means that the electric potential has increased, and so that was plus. If for some reason we had to go backwards across the battery, then we would have to put in a minus sign there. So we're always just figuring out, is the potential increasing or decreasing when we cross a component. If you're going the normal way across a battery, it increases. If you're going backwards, it decreases. If you're going the normal way down a resistor, then it's going to decrease. And if you're going backwards up a resistor, it's going to increase. Okay, so let's do another example. Let's say that we have a battery and two resistors in series. Okay, so I'm going to call this one 15 ohms, and I'll call this one 30 ohms, and then I'll just keep a 1.5 volt battery over here. Okay, well, I can use the loop rule again. So this time, I'm only going to have 3 points, so I'll put one up here, one here, and one here. Okay, so I'll call this one maybe A, B, C. All right, and so what I'm finding is the potential difference across the 15 ohm resistor, so I'll just call that delta V 15, and then the delta V across the 30 ohm resistor, which I'll call delta V 30, plus the delta V across the battery, and those have to add up to 0. Okay, so I don't really need to name the points in the circuit. All I have to do is add up every place where it might change. Okay, so what is the potential difference in each of these cases? Well, the potential difference across the 15 ohm resistor is going to be the current through the 15 ohm resistor times the resistance of the 15 ohm resistor. Okay, because we're going down the resistor, so the current goes this way, and then this way, and then this way, this will end up being negative. So anytime you're going around the circuit in the same direction as the current, the potential decreases. Okay, what about the 30 ohm? Well, we have whatever current is going through the 30 ohm resistor times whatever the resistance of the 30 ohm resistor is. And again, it'll be negative because we're going with the current around the loop. What about the battery? Well, we're going the normal way across the battery, so just plus the 1.5 volt potential difference. Those all add up to 0. Okay, so it looks like we have a bunch of unknowns here, but we know the two resistances. And it turns out the currents are the same as well. So if you consider point B in the circuit, whatever current leaves the 15 ohm resistor is the same current that enters the 30 ohm. So the same current is throughout. Right? So what this looks like is negative I, because there's only one current to worry about, times 15 ohms minus I times 30 ohms plus 1.5 volts equals 0. Okay, and you can solve for I, so negative I times 45 ohms plus 1.5 volts equals 0, and the current is going to come out to 0.033 amps. Okay, so this is another case where we use it. So essentially all we've done is apply Kirchhoff's loop rule and Kirchhoff's junction rule in a couple of cases. You take a loop in your circuit, add up all the potential differences, they come out to 0. We replace the potentials across the battery with plus or minus the EMF of the battery. We replace the potential differences across resistors with plus or minus I times R, and then we solve for currents. That's the basic idea.